So I think by now you've all realized that there's a problem with the fact that I asked you whether light is a particle or a wave, and there were even some people that suggested that it was both. So we're going to quickly look now at who was right, and you will see that it is actually a particle as well as a wave. And the wave nature is easy to confirm. So the people that were doubting the wave is kind of worrying because you'd spent a whole topic in grade 10 looking at light and how it is a wave. And we confirmed the wave nature by all looking at all those things. So you looked at the reflection of light, you looked and saw that incident ray is equal, or the incident angle is equal to the reflected angle. You looked at mirrors and you were drawing images and all of that. So light definitely gets reflected like any other wave. You also looked at refraction. So some of you will remember the fishes that you had to draw under the water. But what's also important is that light bends then through a prism, and that's what gives us this rainbow effect. So this is also an example of refraction. And then we didn't really look at interference. It was in your books, but interference is when two waves cross each other and they form a bigger wave. By doing that, light definitely does that, because we can see that by the fact that when we have light passing over the same split here, so what you can see here is there's a split there. So there's a wave coming from this side and a wave coming through from this side. Some of you drew this and some didn't. You get bright spots and dark spots. You don't need to know the detail of the interference, but the waves interfere with each other, and the bending of light here is diffraction. So this is actually showing interference as well as diffraction. So it's the diffraction pattern that causes the light to do this. And you will remember that someone asked, how do we determine the actual wavelength of the wave? And when you go to varsity, you'll actually do experiments, doing double slit experiments. And according to the distances here, you will then be able to see what the wavelengths of these waves are. So yes, light is definitely a wave, and we have confirmed that. Now, if we look at light again, if you are lying in the sun and the sun's waves are hitting you, if you are lying there for a second, you haven't absorbed any energy from the sun. If you're lying there for a longer and longer time, you're absorbing more and more energy from the sun. So we know that waves transfer energy. That they already knew. Now there were some things, and the main one is then the photoelectric effect. Some things, some phenomena could not be explained just using the normal wave theory. And Einstein's photoelectric effect that won him a Nobel Prize was the main one. So photoelectric effect, super important for this chapter, because the photoelectric effect then made them wonder about the wave nature of light. So I'm thinking again about lying in the sun. What they already knew about electrons. So what I'm showing you here, these are electrons here in a metal. So you know already at this stage that electrons in a metal are delocalized. So what can happen if I give them energy? So you can just see these waves as energy. These electrons can gain enough energy to leave the surface of the metal. So you can give them energy in any way. You can heat them up. And once they have enough energy, they will leave. So what they were expecting, if light was just a wave, what should happen is, like you lying in the sun, electrons should be gathering energy from this wave that hits it. And at some point, when it has enough energy, it must leave. All right? But then when they did these experiments, they realized that there were some energy waves, some low energy waves, that could never, ever, ever emit these electrons. So using the wave theory, they could not explain that. So they started thinking already, is light actually just a wave? Then the next thing that was happening is there was no time delay. Remember, if you're lying in the sun, for the first 5 minutes you are not burning. So you have to lie there for quite a while, and then you're getting hotter and hotter and hotter, and if you've had enough, you will leave. So That did not happen with the electrons. If the wave did emit an electron, the electron immediately left. So that could also not be explained using the wave nature. And then the last thing that the wave nature could not explain is that these electrons that were leaving, some of them were very fast and some of them were very slow. And they could not explain that using the wave theory, because if you were lying here, all of you or all the electrons should get fed up with the sun at the same time because they've now had enough, and they would be leaving with the same amount of energy that they've gained from the sun, and that did not happen. So now they had to think about light in a different way and think, isn't it maybe a particle as well? Because when they did this, and this is now super important, when they did this, for the photoelectric effect, the observations that they made that led to the fact that it was actually a particle as well, is they saw that as soon as the light hits, it immediately send out electrons. So immediately all the not all the electrons, but electrons would be leaving. Then also what they saw is that some waves, like I said, so for instance, a red light would not emit any electrons. So even if I make that red light very intense, I make a very, very bright red light, electrons would still not be emitted. So that a phenomenon of the photoelectric effect they could not explain using the wave theory, or that observation they could not explain. And then that the electrons left at different speeds. So they saw all these different things. They saw it happens immediately. They saw electrons were leaving at different speeds, and they saw that some lights could emit electrons and some lights not. And now we need to think about the particle theory. So this is what Einstein then said. He said, fine, let's look at light in a different way. So we know already that light has energy. And from the previous lesson, we know that this energy is equal to H times F. So the energy that the light comes in with is a specific energy that we could calculate, because we've done it now in the previous lesson. Now, when these particles hit, for it to go immediately, or for electron particles to leave immediately, there has to be a one-on-one particle interaction, almost like a car hitting another car, or a snooker ball, pool ball hitting another ball. So what happened, what he then said, let's see light as little packets of energy. So these packets, if it's a specific color of light, and you've been doing these calculations, so if it's red light, oh, let's make it green because they're written in green. If it's green light, it will have a specific amount of energy. And that specific amount of energy we call quanta. So a quanta of energy belongs to each of these little particles. And we had to give these little particles names, and they called them photons. So these little bundles of energy that light that travels in the light wave is then called photons. So they each have specific amount of energy. So when they hit this electron, they transfer all their energy to the electrons. Because they're packets of energy, they don't keep anything themselves. So they transfer all their energy onto the electron. Now, we're going to look at the calculations in the next lesson. But if this green light doesn't have enough energy for this electron to leave, it won't ever leave. It doesn't matter how many of these green photons I send, if each of them do not have enough energy, they will never be able to send an electron out. Like I say, we'll do the calculations later. Now, if they do, now that's the thing. So if I now go and use a blue light, this blue light will have a different energy, which is also HF. So the blue light's HF will be higher than the green light's HF. And if you look at the video again of the electromagnetic spectrum, you'll know blue, or the violet side, has more energy. So now here comes a little blue photon with more energy, and it hits this electron, and now it gives that electron enough energy to leave. And now every single blue photon that hits will have enough energy, and they will all then emit electrons, kick out electrons from their position. Now, what determines the amount of energy that this electron needs? And this is now where you need to focus, because each metal has a positive nucleus and it has electrons moving around, remember? Now, for each metal, these outside delocalized electrons will be at a different distance from the nucleus. So, if they're very close to the nucleus, they will need more energy. The further they are, the less energy they need. So, if you look at your periodic table, the metals at the bottom have many energy levels, and those electrons are far away. So it's much easier to remove them. So the energy that they then would need is much less. So you will need light of a lower energy or a lower frequency to emit that electron. Remember, energy and frequency is directly proportional to each other. So now to emit this blue electron, I needed that blue energy. But the energy is different for each metal, and we need to give that a name. So the energy needed, we're going to call the work function. You'll see sometimes it's WF, but it's also sometimes the symbol used is W with a little 0 at the top. So the work function, that's the symbol for the work function, is the amount of energy. Please remember, work function is energy that the electron needs to be emitted. Now, if my light has enough energy, I would say it has enough energy to overcome the work function. But because the energy and the frequency is related, we can also explain this using the frequency. So the frequency, that is the exact frequency equal to the work function. So if I have the exact energy that is equal to my work function, that now can just let an electron be kicked out, then this frequency is the minimum frequency needed to emit that electron. And then this frequency that the light has is called the threshold frequency. So please remember, when you're referring to frequencies, to stick to frequencies. And when you're referring to energies, stick to energies, because you're going to get an explanation question on this. And they are going to say to you, why did the green light not emit an electron, but the blue light did? And then you can go at it in two different ways. You can say the green light did not have enough, and then we go the energy route, did not have enough energy to overcome the work function of that metal, because it's both energies. If you go the other route, you're going to say that the light or the radiation did not have a high enough frequency to overcome the threshold frequency. So please make sure that when you explain this, you choose either the energy route or the frequency route, and you do not mix them up. The definitions in this section is also super important. So make sure you know the difference between the work function energy, which is the minimum energy that an electron needs to be emitted, and the threshold frequency, which is the minimum frequency that the light would need to be emitted. And we're going to look at the calculations for this in the next lesson.